Hello, my name is Emily Price. I'm currently completing a Bachelor of Exercise and Sports Science at the University of New England. I am completing this presentation as a part of an assignment for EXSC335 Motor Control and Human Development, which is coordinated by Dr. Dominic McNeil. The topic for my presentation is based upon a laboratory activity relating to speed-accuracy trade-off. Speed-accuracy trade-off is the theory that as the speed of a movement is increased, the accuracy of that movement is decreased, and vice versa. So when an individual is trying to move faster, they are unable to use feedback and make corrections to that movement, therefore making that movement less accurate. Now, as speed-accuracy trade-off is such a regular occurrence in movement, there is a law that relates to it. This law is known as Fitts' law. Fitts' law applies to spatial accuracy, meaning manual aiming tasks. Paul Fitts, 1954, used a tapping task where he manipulated the distance to move and the target size. His findings indicated that the movement time for aiming tasks involving speed and accuracy were determined by distance and the size of the target. An example of a practical application in regards to speed-accuracy trade-off would be performing a tennis serve. A tennis player has two serves to hit their target, which is the service square, and generally speed is the preferred approach in the first serve. If the target is missed in that first serve, the movement is slowed to some extent in the second serve, so the tennis player can ensure to hit the target. There are two primary types of control within motor control. These are open and closed loop. Closed loop refers to the individual receiving feedback during movement to detect and correct errors so the individual can adjust and modify their movements if needed. Open loop involves the initial movement instructions containing all the necessary information needed to carry out that action as intended. Therefore, feedback is not used during the execution of the movement. Open and closed loop control were both seen within the laboratory tasks discussed within this presentation. To investigate speed-accuracy trade-off, external EXSC335 students completed a laboratory activity involving two tasks. These two tasks looked at whether speed-accuracy trade-off occurred in spatial accuracy and manual manipulation. The first task that was completed involved a throwing task. In this task, participants were required to complete 10 trials of underarm throws with a tennis ball to 3 different target sizes. These target sizes were categorized as small, medium, and large. The target that was used for the activity was a paper archery target that was pinned to the wall, and there was a marker that was placed 3 meters from the target. This marker was where the participants were instructed to throw. The hypothesis for this task was that as the target size decreases, the speed at which the participants threw the ball would also decrease, as they would be trying to be more accurate with their throws when trying to hit the target. The second task that was completed was an assembly task, which involved a Purdue pegboard. The participants were required to complete 3 trials where they were to place as many pegs as possible into the pegboard in 3 conditions. These conditions were using both hands to complete the task, using their preferred hand to complete the task, and using their non-preferred hand to complete the task. Each trial was to last 30 seconds. It was hypothesized that for this task, using both hands would result in the most pegs being placed in the pegboard. It was also hypothesized that the participants' preferred hand would result in a greater score than their non-preferred hand. So in regards to the first task, which was the throwing task, the group data showed that speed-accuracy trade-off did occur. The small target had an average of 6.77 hits out of 10 trials. The medium target had an average of 7.69 hits out of 10 trials, and the large target had 7.92 hits out of 10 trials. This data can be shown in the graph here. The data shown in the graph demonstrates that as the size of the target decreased, so did the participants' accuracy when throwing the ball. It was observed during the task that as the size of the target was decreased, the participant would focus more on the accuracy of their throw, thereby disregarding the speed at which they were throwing in an effort to gain the highest score possible in the task. This reinforces the hypothesis for the task that as the target size decreases, the speed at which the participants threw the ball would also decrease, as they would be trying to be more accurate with their throws when trying to hit the target. At the beginning of the task, closed-loop control was displayed as the individual made little to no adjustments to their movements to complete the task. However, towards the end of the task, when the target got smaller, the individual made slight adjustments to their movements in order to be more accurate and ensure that they hit the target as many times as possible. This suggests that it may have shifted from open-loop control to close as the task got more difficult. Now, in regards to the second task, the assembly task, which involved the Purdue pegboard, the group data showed that speed accuracy trade-off also occurred. When the participants were using both hands, they produced an average score of 16.06. Using their preferred hand, they produced an average score of 13.19, and using their non-preferred hand, they produced an average score of 11.91. This data can be shown in the graph here. The data shown within the graph demonstrates that the participants were more efficient when using both hands to manipulate the pegs into the board, and when comparing participants' preferred and non-preferred hands, it was shown that their preferred hand was the most accurate. The pegboard task became more complex when the participant was just using one hand, either their preferred hand or their non-preferred hand, and the participant had to slow down their movement in order to be more accurate when placing the peg into the board. This reinforces the hypothesis that using both hands would result in the most pegs being placed into the pegboard, and that the participant's preferred hand would result in a greater score than that of their non-preferred hand. This task was representative of a closed-loop control. As each trial went on, the individual would receive feedback and constantly make adjustments to their movements in an attempt to fit all the pegs in the board correctly. The data shown within this task is depictive of the dynamic systems theory. The dynamic systems theory involves the individual modifying their movements in response to change in environment. This was evident in the pegboard task as the individuals modified their movements to fit the pegs in the different holes. The change in the environment being the different shaped holes in the pegboard. In conclusion, the data collected within the laboratory tasks has shown that speed accuracy trade-off has occurred and can also be seen to support previous research regarding speed accuracy trade-off. However, there were some factors within the tasks that may have influenced the results that were produced and in turn reduced their reliability. For example, in regards to the throwing task, a human error was identified as a possibility that could have affected the end result. This was because the individual throwing the ball was solely relying on their partner's reaction time in the activity as they were timing them with the stopwatch. A factor that may have influenced the results and was observed in both tasks was fatigue. Completing the number of trials for both tasks could have taken a toll on the individual and their fatigue levels, which in turn could affect their end results as they weren't as fast or accurate as they could have been. I hope you have enjoyed my presentation and I thank you very much for listening.